Now let's consider that mass spring oscillator problem from lecture where the system is having an external force of the quantity 5 sine t plus 5 cosine t applied to it, where the mass is unit 1, spring constant is 2, and the friction has the value 2. So we know how to construct the corresponding left-hand side of a second-order linear differential equation, but now with the forcing function it becomes non-homogeneous because we have 5 sine t plus 5 cosine t on the right-hand side. We have these initial conditions, that the initial position of the mass, as you can see illustrated in the diagram, is at position 1, equilibrium would have been at 0, and that the initial velocity is 2. Our goal is to find the equation of motion, and what we want to do is apply superposition, because we'd like to solve the equation as if the right-hand side was 5 sine of t, then turn around and solve it as if the right-hand side was 5 cosine of t, and then be able to combine those two solutions to get the particular solution for this. But keep in mind the general solution, as we talked about in lecture, is a particular solution plus the solution to the homogeneous system, which has arbitrary constants, which can be determined by these initial conditions. So let's go ahead and work on the homogeneous case first. That's what you should do. So, of course, the homogeneous equation is just the left-hand side set equal to 0. And we know from second-order linear homogeneous systems we need to look at the roots of the auxiliary equation. So if we write just briefly what the auxiliary equation would be, we would have r squared plus 2r plus 2 equals 0. And using the quadratic formula, it wouldn't take us long to realize that the roots are basically going to be -1 plus or minus I. Okay? So in other words, root 1 would be -1 plus I, and the second root would be -1 minus I. So if we go back, remember for our second order linear homogeneous system, if we have complex roots of the form a plus or minus beta I, we know how to write down the solution, which involves exponents and sine and cosine terms. For this particular auxiliary equation, clearly the alpha is equal to -1, and the beta term is +1. Because remember, the roots are always going to be of the form plus or minus beta I. So in this case, the beta is just 1. So we know then that the solution for the homogeneous equation, if we write it over here as y sub h of t, we immediately know it's a constant, say c1, times e to the minus t, because alpha is -1, times cosine of t, because beta is equal to 1, so it's just 1 times t, plus c2 times e to the minus t sine of t. So we've got the homogeneous solution for this particular mass spring system, but now we need to go ahead and find a particular solution. And again, we're going to apply superposition as if we were looking at, first of all, the right-hand side just being this part. Maybe we'll call it f1 of t. And we'll look at the second part being just f2 of t, like this. Okay? So we're looking at first considering the right-hand side being 5 sine of t, then consider the right-hand side to be 5 cosine of t, get those two particular solutions, and use superposition to find the overall particular solution to this system. Okay? So let's go ahead and write the system corresponding to 5 sine t. Again, what we have is y double prime plus 2y prime plus 2y equals 5 sine of t, which again is what we're considering to be the first functional part of the original right-hand side. And of course what we need to do is consider a particular solution for this, and of course we go back to our method of undeterminate coefficients when the right-hand side takes on a form of a constant times a sine. we should guess that our particular solution, let's call it y sub p1, so it's the particular solution of the first part. We should take, just say a constant, we'll say a times sine of t plus b times cosine of t. Okay. Again, that's by the method of undetermined coefficients. Our goal is to take that guess of the form, take the appropriate derivatives, plug it in the left-hand side, and see if we can pattern match to figure out what a and b would have to be. So again, if we take the first derivative, this function, y sub p1 of t prime, derivative of sine is cosine, so we should have a cosine of t. Derivative of cosine is minus sine, so we're going to get minus b sine t. And again, you need to go ahead and do one more derivative, y sub p1 double prime of t. Taking now the derivative of the first derivative, derivative of cosine is minus sine, so you're going to get minus a sine t. Derivative of sine is cosine, so you're going to get minus b cosine of t. And again, what we do with the method of undetermined coefficients is we now plug these expressions into the left-hand side and set it equal to that 5 sine t. So if we do that, we'll have, just writing these quantities down, minus a sine t minus b cosine t for the second derivative. All of that be added to 2 times the first derivative expression, a cosine of t. That should be minus b sine t. And then what we'll have to do is add 2 times our solution, our guess for the solution, which is a sine t plus b cosine t. And that all has to be equal to 5 sine t if it solves the equation up here. Now it's just a matter of collecting all the terms appropriately, the sine terms and the cosine terms. Let's go ahead and do that very quickly. You can see that if you matched all the sine terms and you reduced it, you should get something like a minus 2b times sine of t. You can see that because you're going to have a minus a sine t here, a plus 2a sine t there, so it gives you a net a, and then you'll have this 2 times minus b there. Similarly, you will have the quantity b plus 2a times cosine of t, and that will have to be equal to 5 sine of t. Pattern matching here, obviously these two are going to have to be equal to 0, and these two are going to have to be 5 for the left-hand side to equal the right-hand side. So therefore we have 2 equations and 2 unknowns. We have a minus 2b has to be 5, and we also know that b plus 2a has to be 0. And of course, to solve that, there's a couple of different ways you could solve it. You could say, well, I know immediately that b has to be equal to minus 2 times a, then plug that into the first equation. That says a minus 2 times minus 2a has to be equal to 5. So that implies that you have a minus minus is plus 4a equals 5. So clearly a has to be equal to 1. And then similarly, if you know that a is 1, this other equation right here immediately tells you that, well, if a is 1, then b has to be negative 2. So what we have figured out is when you just have the first part of the original right-hand side, 5 sine of t, that part of the particular solution, yp1 of t, will have to have the form sine t, we'll write it this way, sine t minus 2 times the cosine of t. Okay? Like that. So, what we're missing is another part of the particular solution when the right-hand side is 5 cosine t. Right? So again, what we're looking at in that particular case is to say, all right, what if the left-hand side was the same, but now we had 5 cosine of t, which is that second part of the right-hand side. And go through the same exact procedure. You'd say, well, we would guess the particular solution here. We'll call it y sub p2 since it's our second part of the overall particular solution. Using the method of undetermined coefficients, we could immediately say that, well, it'd be the same guess, a sine of t. Of course, these constants will be replaced, but we can go ahead and use a and b again. And this, of course, is same process we had before, where we're going to compute first and second derivatives, plug it into the left-hand side here, set it equal to 5 cosine of t. And just to save time here, what that will turn out to be is 2 sine t plus cosine t. Now, if we apply superposition, what that tells us now is we have a solution when the right-hand side is 5 sine of t. We have a particular solution when the right-hand side is 5 cosine of t. So then by superposition, the overall particular solution we need is adding y1 piece of 1 of t to y piece of 2 of t. And in this case, we go back from what we had earlier. We determined that the first component here, the y piece of 1 of t, that is going to be sine t minus 2 cosine t. And we're going to add to that what I just gave you, that the second particular component as a solution would be 2 sine t plus cosine t. Now, just adding those two terms up, you can see what's going to happen. You're going to get 3 sine t minus cosine t. So, the general solution, the equation of motion in this case, then is our homogeneous solution plus our particular solution. Okay. So, in this case, what we'll have, we've already written this down before, we'll have C1 e to the minus t cosine of t plus C2 e to the minus t sine t, and then we'll add this particular solution, 3 sine t minus cosine t. And we would be done, except for the fact that for this particular mass spring oscillator, we know what the initial velocity and the initial position are, and we should use those information to determine C1 and C2. So let's do that in our next part of the problem. So again, let's write down what we have. Making some room here for our oscillator problem here. We now know that the general solution has the form y of t c1 e to the minus t cosine of t plus c2 e to the minus t sine t plus the quantity 3 sine t minus cosine t, which was the particular solution. We know that y0 is equal to 1, and we know that the derivative at 0 is equal to 2. So let's go ahead and use that first initial condition. That says when we plug in 0 for t, we're supposed to get 1 back. Look up here very carefully, you can see what's going to happen. When you plug in 0, e to the 0 is all 1s. So e to the minus t, e to the minus 0 is still going to be 1. The sine t's will wipe out, so there won't be any sine t's left, because sine of 0 is 0. So what you're going to end up, in this case, is just c1, this term will be 0, that's 0, and you're going to have c, then you're going to have cosine over here is 0, which is minus 1, so you're going to have c minus 1, like that. So obviously, if 1 is to be equal to C1 minus 1, we have to have that C1 is 2. Okay? So we almost are done. We found that C1 is equal to 2. Now let's use the second condition. To do this, we're going to have to compute derivatives. Because the second condition is based on velocity, so let's compute the derivative of y of t. Let's do that. What would y prime of t be? Well, we're going to have C1, then use the product rule. First times derivative of second, plus second times derivative of first, so it'll be minus t times minus sine of t, plus cosine of t times minus e to the minus t, so we've got to be very careful with our signs. The next part, plus c2 times what? E to the minus t times cosine of t, plus sine of t times minus e to the minus t. And then the other parts would just be plus 3 cosine of t, and then since the derivative of the cosine is minus sine, we'll just get plus sine of t. So we could maybe clean this up just a little bit before we apply the initial condition. Let's do that just for a second. So what we've got is that the derivative would have to be quantity C1, right like this. You have minus cosine t minus sine t. You're going to, let's write it this way, minus sine, or minus sine t times e to the minus t, minus cosine of t, e to the minus t. And then over here we'll have plus c2 times, we can write this as minus sine t, e to the minus t, plus cosine of t, e to the minus t. And then again we have our the remaining terms, 3 cosine of t plus sine t. A little bit easier to work with. So let's go ahead and plug in what the condition says, that the initial velocity says to be 2. So when we plug in 0 for the derivative, we should get 2 back. So let's go ahead and plug in 0 and see what happens, see what gets wiped out. Keep in mind that the sine terms will all wipe out completely. So this term will be gone, this term will be gone. So we're going to have C1 times, this will be cosine of 0 is 1, e to the negative 0 is 1. So we're going to have c times minus 1 plus c2 times, let's see, this term will be wiped out because sine of 0 is 0. That'll be a positive 1. So we'll have plus 1 here. Then we'll have 3 times cosine of 0, which is going to be plus 3. But the sine term will go away. So what we've got is 2 is equal to minus c1 plus c2 plus 3. Or, you know, we could pull terms over either side. If we subtract 3 out, minus 1 has to be minus c1 plus c2. We already know that c1 is equal to 2, so minus 1 equals minus 2 plus c2. So that implies c2 equals 2 minus 1, which is equal to just 1. So, finally, we're there. The equation of motion has to be, we just said that c1 is equal to 2, so we'll have 2 times e to the minus t, cosine of t, plus, we said c2 is equal to 1, so we'll just say plus e to the minus t sine of t, and then add that particular solution, 3 sine of t minus cosine of t. There you are. That is the equation of motion for that mass spring oscillator. What's real interesting to note is that as t grows and gets larger and larger, this term's going to get smaller because that's going to be 1 over e to the t. Ultimately, as time increases, this part of the solution is going to dominate. And it's real interesting if you look at the graph of this, as t starts from 0 and continues out towards infinity, that you can clearly see this is the part of the solution that is going to dominate, and it dominates fairly quickly. In fact, I've got a graph of it right here. I'll zoom back out just slightly so you can see this. If you graph it, here's what you have. Here's the graph of that solution. And the only thing I'd like to point out that I'm going to zoom in just a little bit on so you can see what happens early on. Right before time becomes unit 5, right here. What you'll notice is that this part of the solution in blue right here, this is the original solution curve. This part right here, that's the initial condition. It starts off here. And then after, a little bit past 2, it's totally dominated by just the 3 sine of t minus cosine t curve. So the rest of this curve is just 3 sine t minus cosine t. It's only this portion that corresponds to the entire general solution. So very quickly it turns into that steady state sort of oscillatory 3 sine t minus cosine t, just barely after 2.5 seconds, something like that. Very interesting. And if you zoom out again, you'll see the whole oscillatory nature. It's just going to keep oscillating like this. That's what the solution would do.